Okay, we are recording. I don't know what happened last time. I swear I was recording, but something, I think I got messed up. Oh, it's bright. Okay. Everything organized here. Wait for a couple more people to come in. All right. Too many windows open here. I gotta close some of these windows. Okay, I have some the practice document up, and I just posted an extra practice in case we need something to do to fill the rest of the time. We have homework due tonight in my stat lab. I haven't been getting any questions from there, so maybe we can ask some of those now if you want to. And then we have our quiz on chapter 10 will be this Friday, like we've been doing. That'll be in D2L. So let's open it up. Anybody have any questions that you wanted to ask? Oops, let me get in the right course here. Any questions to get us started? Seems quiet. Standard deviation. So let's ask about how you know the conditions are met, and this would be for the same conditions for confidence intervals from chapter 9, and then also for hypothesis tests. And so her question is about the conditions for the mean and for the standard deviation. So let's take a look here. I'm going to open up the online lesson. Let's see here. So content, because they're in the videos sometimes, but everything is definitely in the online lesson, and then it's in print form. You can kind of see it there. So let's look proportion. Let's just review this while we're in here. For proportion, let's see here. So the conditions here, this is all based on the sampling distribution of the sample proportion. You have to have less than 5% of the population, and then the n times p times 1 minus p has to be at least 10. So that's the check for the p hat for 10.1. All right, let's go over to 10.2. Hypothesis test for population mean. So there are two things here. One is it has to be from a random sample. So the sample is obtained using simple random sampling. The sample has no outliers. And then there's an or here. And this is the key. Either the population from which the sample is drawn is normally distributed, and you can be told that in the problem, or you can check that by doing like a normal probability, the QQ plot, or a histogram. You can do there's some more rigorous checks which are kind of beyond this class. But either the population is normally distributed or the sample is large. And that n greater than or equal to 30 is not like this super hard line. It's a little fuzzy, like a lot of statistics. It's like, well, there are a couple options here. So you're like, my green screen is broken. I'm like, you can see beyond my green screen. So it's an or between those two things, and that's what I think most people struggle with is how do I know, do they both have to be true? I know someone had emailed me about that, and it's an or. Either the population is normally distributed or the sample size is large. Then if we look at the standard deviation, does it show it in here? It talks about the chi-squared. So it doesn't say here, does it? Shoot, it doesn't have the condition here. So the condition for the population standard deviation, gosh, it's been a while here. I think that the population, yeah, here we go. So this is it's here in the conditions of the chi-squared distribution, but it's not really here in the conditions for the test. But up here in the condition for the chi-squared distribution, if a simple random sample of size 10 is obtained from a normally distributed population. So the result is here that the sample size greater than or equal to 30 isn't enough. To do the test about the standard deviation, you have to have a normally distributed population. So you either have to be told that, or if you have sample data, you can do a QQ plot or a normal probability plot. Does that help, Alyssa, or did you want to do a couple of examples too? Okay. All right. Because I think it says that right in the practice document. I believe it says that for everyone, you're going to do this test. Are the conditions met? You're going to do this test. Are the conditions met? If you're going to do this test, are the conditions met? Are the conditions met? So it asks you that every time. So for this, what is this one? Right, so this one we're not told anything about the data, so we don't know it's normally distributed. So we'd have to either hope the sample size is large, or we would do like a QQ plot and a histogram to see if the distribution is approximately normal. Here we have like a large sample size, 600 faculty members. So that one should be good. So those are the things that you are checking here for these as you go through here. Okay, any additional homework related questions? Number 6, let's take a look here. Average faculty salary is about $6,180 with a standard deviation 2,500. Using the scholar scorecard data, we can see the average faculty ECC is approximately 10,200. Okay, if we use the fact that there are about 600 faculty members, is there enough evidence to say that the average salary ECC is greater than the national average? Interesting here. So we actually do not have it, do we? Right? So we have a couple of options here. This might be one of these. This isn't really clear, is it? Let's see if we get different results. We have two options. This might be one of the rare options where we could say, you know what, let's assume the standard deviation is the same as the national. So like, let's assume that we have sigma, that we have the population standard deviation. So then we could use a z-stat instead of a t-stat. I don't think the results are going to be very different, and I'll tell you why when I'm done. The other thing we could do is we could say, you know what, we don't have a sample standard deviation. Let's use that 2,500 as our sample standard deviation. So let's try that. I should have, yeah. I'm just gonna, doesn't really matter. Actually, I don't need to open the data set. I'm just gonna open StatCrunch. And let's try both. We don't use the z-stat a lot. We talked about this because the z-stat is like you have to know the population standard deviation, which you usually do not. So we're going to do with summary. And we have our sample mean is given to us 10,200. 10,200. And I put a note there that seems like a really small salary, and that's because it includes, like the majority of our faculty actually teach part-time. They teach a couple of classes a semester with us. So that's why the sample mean is so low. There's not, I think only 30 some percent, like less than a third of our faculty are full-time. Actually less, yeah, much less. It's like 140 out of 500 or 600. Yeah. Standard deviation, we're going to use 2,500, and then our sample size, I believe, was 600, wasn't it? About 600 faculty members. Is there enough evidence at the 5% level of significance to say the average salary is greater than the national average, which is 6,810? So I'm going to say The alternative is that it's greater than, and not 0, 6,810. So the null hypothesis is that it's equal to that, not different. And then the alternative is that it's greater than 6,810. Okay, any questions so far about putting all these values into the unusual here using a z-stat? Any questions so far? All right, we'll hit compute, and I'm going to save this off to the side here. You'll notice, by the way, our mean is way higher than the 6,810. So we got a really high z-stat, and basically a probability of getting our mean is almost, it's impossible. It's not impossible, but it's really, really unlikely. And so that's why I don't think it matters. Let's do a t-stat with summary and do all the same stuff. And this is to Daniel's point, how do we get the sample standard deviation? We don't have the sample standard deviation. Yeah, and I see, Daniel, you got the same things. I'll talk about why. Maybe you know why. There's a mathematical reason why they're not different. They have all the right things there, 2,500, 10,200, and then greater than. And then we compute. And you'll notice here, check this out. Z-stat, 33.2, T-stat, 33.2. You're like, what? What? How are those the same? There's something happening here in the background that we haven't talked a lot about, and that you wouldn't really totally understand why, and that's okay. If we go back to when the T distribution was first introduced, which would have been in chapter 9. There's this T distribution. It's basically, it looks normal. You can see here's a Z, here's a T. They're almost the same. And then as the sample size increases, the distributions become more and more similar. And when you have a large sample size, a T is basically the same as a Z. And so that's why you notice that, Dan, that's why you got the same thing here, is because we had 600 as our sample size. So it really doesn't matter which one you use when you have a sample size of 600. The main difference is when sample sizes are like close to that 30 cutoff, like 30, 50, 20, somewhere in there, then it'll make a bigger difference. But it didn't really matter here. So this one is interesting. It's kind of, the directions are a little unclear here. It doesn't really tell us to use the 2,500 as our sample standard deviation. I was just working on an example for today, and I said, oh, if we assume the standard deviation is, and like I told you what to do, but this one I did not. That's a little unclear. What do we think? Let's go ahead and finish the problem. Do we think the average salary at ECC is greater than the national average, statistically greater? Why don't you, did we talk about how to vote yes or no? You can actually, if you click on participants, then there's a little green check or a red X. Can you see this? If I show you this, little green check and a red X, you can click on that and you can vote yes or no. So the question is, do we think the mean is statistically, at ECC, is statistically greater than the 6,810? So you just click on participants and then you can vote yes or no. It's a quicker way to do a poll if we're only doing yes or no. There's also other ones you can do too. You can like clap, yay, clapping, or I need a coffee break. Dislike, oh, that would be rude. All right, so it looks like we have 5 people said yes, nobody said no, maybe still thinking. And yeah, that is correct. That is correct. Because we have that really low p-value, essentially what we found is, the 6810 would be the mean, the national mean. And I don't know if my video is flipped or not. So what did we have, 10,200 is way off screen. It's 33 standard deviations away, right? It's a Z of 33. or a t. So it's 33 standard deviations away. It's like super, super, super high. And so that is really, really unlikely to happen randomly. So we would say, yep, our mean is statistically higher than the national average. Yeah. All right. Good. Okay, good question, Daniel. Thanks for bringing that one up. That is definitely subtle on that one. Yeah. All right. Any additional homework questions or questions from the practice? All right. Question what, number 8? Any particular part of this one, Daniel, or do you want to just work through it from the beginning? Sorry. Just doing the actual test. Yeah, I think it's a little tricky here to get like just those students. So let's read the question carefully. Let's see if we wonder if the heights of 12-year-old boys, if they're more spread, if the standard deviation for them is more than the heights for boys of other ages. So we calculate, and I actually did this, we calculate the standard deviation for boys of other ages. It's about 5.4 inches. First of all, are the conditions met to perform a hypothesis test? They must be normally distributed. So let's create that histogram, but we want to get just boys ages 12. So let me go into StatCrunch and my groups. We've got our spring group, and there should be the health. Oh, where did that one go? There we go, health behaviors in school-aged children. Okay, we want to do a histogram. Let's make that. Make sure you are practicing titling all these too, because when I ask this question on the test, I'm going to want a title, so don't forget to do that. By the way, I apologize for your tests. They are still in progress. Everything is taking longer now. I'm like behind and I can't get caught up. I'm sure some of you know the feeling. Okay, height. Now I want to just get 12-year-old boys. Now I did give a hint there, but I think maybe I'll just build it. Now we should be able to type it. Where, okay, what do we have? We have gender. So we're going to say where gender equals male and, oh, is it age? Oh, I can't see. Let me go back over to my practice document. Age equals 12. And that should just get us 12-year-old boys. And let's title it ages, or not ages, they're all 12-year-olds. Heights of 12-year-old boys. Compute. When we get that, it's not bad. It's a little skewed left. One of the things we say about this test is it's fairly robust. So the test is, it doesn't have to be perfectly normally distributed, but this one would definitely make me a little nervous because it's a little skewed left, but you know, it's one of these things where we'll kind of, it's hard to know when you're doing these because when you get to the quiz, there'll be an option for you to check that the conditions weren't met. But this one I would say is like close enough. It's not like some of the variables we've looked at where they're really skewed one way or the other. So we'll say the conditions are met closely enough. Is there sufficient evidence to state that the ages of 12-year-old boys are less spread out? So that means we think the standard deviation is less. So let's go to StatCrunch. Where do we go to do tests about standard deviations? There's nothing on here about standard deviation. So Daniel's filling up the chat here. Variance stats is correct. One sample. We do have data. We do have data. So with data. Then let's see here. What are we doing? Height. And then again, we have to type in where gender, because we just want to get, this is our sample data. We want to get just 12-year-old boys. One problem here is this is variance stats. This is sigma squared. So it's not 5.4 here. It's not what we're going to test. We need to get the variance. So we just literally square it. And you can just type in that little caret symbol, or you can type it on your calculator or something in 5.4 squared. And we think our variance is less than that. That's what we're testing for. Now, the nice thing here, when you do this test, remember when you did the confidence interval, it gave you a confidence interval for the variance and you had to do the square root. This is just going to give you a p-value. You just interpret the p-value. You don't have to take the square root of the p-value. It's not a square, it's just the probability. So you should just be able to hit compute and then interpret your p-value here and go from there. So it does look like they are more like less spread out, which makes sense if you could look at all other ages. Well, then you're looking at ages, I don't know what the smallest age is, 5, all the way up to 13. I don't know what the age range is, but it would make sense that that height standard deviation would be wider than just looking at a single age. So that it makes sense that it should be less spread out. We do get a very low p-value here, so we would reject the null and say that the variance is less than 29, or the standard deviation is less than 5.4. Did that clarify your StatCrunch question, Daniel? All right, excellent. Any other homework-related questions? Or practice-related questions? I wish the chat had like, I took this class at NIU, I think it was last summer, summer before? It was a class, it was an online class, but we met once a week for 3 hours. We had a nice long break in the middle. It was kind of cool. And we had this, it was kind of like this, like there was no cameras actually. The instructor didn't have a camera either, no cameras at all. And the chat had a little thing though, when someone was typing, it would like Facebook Messenger has, or they're like, you know, so-and-so is typing. So you could kind of know, like, I think it would be nice as an instructor, like, is anyone typing? I don't know. Should I keep waiting? I don't know if someone's typing. So I think that would have been, it would be a nice feature. It was like, it's like Adobe, some kind of Adobe thing, I think it was. Anyway, lots of different streaming ones. I'm not going to switch now. It's too late. We're doing what we're doing. Let's do the practice then. I uploaded one just right before class. I uploaded an extra practice, just two additional examples from chapter 10. Trying to make them a little interesting though. So if you go to the home page, there's a Word document here, and you can click to open that extra practice. And I thought we could just do a couple of different examples together here. So the first one I thought, I was thinking about this. This is just about the virus, the coronavirus, and there's so many uncertainties about it. And one of the biggest ones is like what's the death rate for it? People are freaking out, and other people are like, oh, it's the same as the flu. And it's hard to really know because they have tests for it. When people are in the hospital, they have a pretty good count of deaths. Now, some people are told to go home and then they have a crisis at home and they die and there's no autopsy. And so there's some undercounting of deaths, but like there's a pretty good count of deaths. But there's a lot of people that get sick and don't ever get tested. And so we don't know, you know, it's the denominator. You have this deaths, which is pretty accurate. And you can't just divide by the number of positive tests results, because those are only people who had symptoms and the doctor got them a test and they went to the hospital. Now we're doing more and more testing, but there's a lot of people out there that have had the disease, didn't have any symptoms, and so it's hard to know what the actual death rate is. So one interesting situation here was this Diamond Princess cruise ship. I don't know if you heard about that, but there was an outbreak on the cruise and every passenger was tested So they knew how many were positive from everyone in that particular environment. And many of them had no symptoms. So like half of them were asymptomatic. They had no symptoms. It was something like, it was like 300 and some did not have any symptoms. So there were 696 positive cases on this one cruise ship, and 14 individuals ended up dying. So what I thought we could do is we could do a hypothesis test to see if that's different from the flu death rate. So I looked up the CDC estimates for last year's flu. I've got those links here if you're interested. They had about 35.5 million illnesses, and they have some explanation for where they got that, and about 35,000 deaths. So if you divide those, that's a death rate of about 0.1%, okay? So that's what we're gonna compare with. So we're going to wonder here, based on the Diamond Princess data, is there evidence that the death rate due to the coronavirus, the new coronavirus, I should really call it like COVID-19, right? Anyway, is the death rate, at least for populations similar to those that were on the cruise ship, is it higher than the annual estimated death rate due to the flu? We're going to check the conditions and then perform all 6 steps. So let's do this here. So first, the conditions. N has to be less than 5% of the population. Well, we have 696 is certainly less than 5% of all humans, right? So yeah, okay, we're good. So that's fine. And then we also need N times P times 1 minus P. Oh, it like automatically capitalized. That's annoying. To be at least 10. So let's see here. N is 696. P is 14. No, P is 0.1. We're gonna, or 0.001. That's our P that we're comparing to. Times 1 minus 0.001. I should have done this already. Let's see here. I think we're good. I hope we're good. I tried to make an example that we could actually do. Uh-oh. We're not good. We can't do it. What did I do earlier? Oh, I did. I did my decimal place in the wrong spot. I'm like, I swear this was possible. Okay, so that's like 695. So, oh no, it isn't. It's not right. Times. Oh, it is too small. It's like less than 1. Oh no. The problem is that the 0.1% is so small. We need to have a larger sample size. So what did I do when I tested this earlier and like it totally worked? N times P, I'm not doing anything wrong, am I? Oh no, that's not good. Okay, well, let's just practice. Let's just practice doing the test. So the problem here is that our distribution for our P's, our P hats won't be, for that binomial distribution, won't be symmetric. So like, I'm trying to think of a way to show that. If we do a binomial probability, whoa, why won't it show? Where did the binomial go? Oh, it's up above. Oh, that's annoying. It got like shoved up. Okay, there we go. If we have 696 and P is 0.001, I'm just going to do N is, yeah, so the problem is that our distribution here with this P being so small is not normally distributed. We probably have to have like 60,000. See, you see how when we have there, it's actually approximately normally distributed. It looks like a bell-shaped curve. So the problem is with only 700 is it's very skewed right most of the time. With 0.001, most of the time we're only going to have 0, 1, or maybe 2 people die out of that. So if this was on the practice document for the quiz, we should answer no, the conditions are not met. No, the conditions are not met. Let's practice with the StatCrunch commands, but we won't actually paste it. So that's funny. I swear I checked that before class. Okay, so let's check it though. So let's do, this would be a proportion stat, if we could actually do it. One sample, we don't have data, we just have summary. We just have summary, and there were 14 deaths, if I remember correctly. 14 deaths out of the 696. Oh, that's what I did. So the test that I did is I used the sample proportion, and that was bigger, and that's why it worked. Yeah, that's why. 0.001%. And we wonder if ours, is it just different? Higher than. Based on the diamond, is there evidence that the death rate is higher than the annual death rate due to the flu? So we're wondering if ours is higher. We can actually answer this question, but just not the way we're doing it right here. So if we were to do this test, we would compute, and you can see we would have a very small p-value. We have a very small p-value. So let me show you, we can actually do this. I don't know if there are any examples in your homework. If those conditions aren't met, you can actually do the binomial distribution. So those conditions aren't met, that means that p hat isn't normally distributed, but we can use the binomial distribution. This is just kind of an added example here. The key is that the p-value is the probability of observing our results or more extreme if the null hypothesis is true. Okay, that's what the p-value, it's the definition of the p-value. So our step one is to set the null hypothesis. And the null hypothesis would be that the proportion is the same as it is for the flu. And then our alternative hypothesis, we think it's higher than that. Second step is our alpha level, our level of significance, and we were told to, is there evidence that the death rate, so it doesn't give us an alpha, we'll use our typical 0.05 then. And then 3, the test statistic and p-value, I'm actually going to skip 3. The p-value, we can do that, this is interesting, it's the probability of getting 14 out of 696 or more if p is 0.001. So this is actually interesting. You can actually use the binomial distribution to do that. Now we have this whole thing in chapter 8 where we approximate the, we get the sampling distribution of p hat and we make it into a normal distribution. We find its mean and standard deviation. And we've been using those that result in confidence intervals and here in hypothesis tests. But if we remember that p-values are just probabilities, we can actually use the binomial probability to do that and actually just do stat calculator. Here it's like zoomed in again. It's so annoying. It doesn't let me scroll up. We can use the binomial calculator to find that probability. If we have 696 people, and the death rate is 0.001, what is the probability of getting at least 14 people die? Look how small that is. Really, really, really small. So what we can say then is this is actually less than 0.0001. That's like the lowest p-values. I don't know how to write that, but that's kind of that notation. You've seen that on StatCrunch. it always does that. If it's never going to say 0, it's just going to say it's really, really small, so it says less than 1/10,000th. So we have a really low p-value. We would reject the null hypothesis. And so our conclusion is, yes, there is significant evidence to support the claim that the death rate due to COVID-19 is more than the death rate due to the flu. Now keep in mind that this is based on data, real data from the Diamond Princess. So this is really only for people who are similar to that population. For populations similar to the passengers on the Diamond Princess. So that's one problem here, is it's not, there's no little kids on there who can get the flu, and not a lot of 20-year-olds. So it's not a perfect comparison. So that example ended up not being as good as I wanted it to. That's the problem with kind of making stuff up here at the last minute. I was working on this right before class. That was an interesting example, and it does kind of show the proportional is the only one you can do this. If your check fails, you can just use the binomial distribution. The other ones, if your check fails, you're out of luck. So that one's interesting. All right, and then I have one more example. This one should be a little bit easier, hopefully. I was looking at school data, and I know all of you, I think all of you are young enough where you all would have taken the SAT. Used to be the ACT, but switched to the SAT recently. I looked up the College Board test scores, and the overall average SAT score was 1,068. And then I just picked the local high school, South Elgin High School. Their average was a little lower than that, 1,003.9. That was based on 592 students. So here's kind of to Daniel's point. Here's what I told you. If we assume the standard deviation of scores is 241, is there evidence that the average SAT score at South Elgin is statistically lower than the national average? So the conditions here, we don't know that SAT scores are normally distributed, but the sample size is 592, which is really big. So we're good. We have a really large sample size there. All right, so null hypothesis would be that the mean, I'm going to use my Greek symbol here, that the mean is equal to the same, 1,068. Oops. Ah. And then the alternative would be that the mean is, are we saying statistically lower than, so less than 1,068. So we are checking to see if the mean is less than that. Again, whoever wrote this didn't give us a level of significance, so we'll use our typical 5%. And let's see here, we need a test statistic and then a p-value. So let's use the StatCrunch for those. Here we are testing for a mean. So we're going to use a t-stat. Now we really could use either one again here because it doesn't really say, is that a population? It's based on statewide data. So maybe this is a z-stat. Again, our sample size is so large, it's not going to matter. They would be the same. So let's do a t-stat, one sample with summary. Sample mean 1,003.9, standard deviation 241, sample size 592. Did I remember all that right? 592, how do I remember all those? 1,003.9 for the mean, 592 is the sample size, and then the standard deviation is 241. Okay, our null hypothesis is that the mean is the same as the national one, and then I'll our alternative is that it's less than that. Yeah, I think we're good. Sample mean, sample standard deviation, which was given to us. We didn't have any data to calculate that. Sample size 592. Our comparison mean is 1,068. We're wondering if we're less than that. So I think we are good. Hit compute. And we have a t statistic, and it's about -6.47. So test statistic t is equal to -6.47. And p-value is very small, 0.00, less than 1/10,000th. Again, very small p-value. And you can see here, you know, it seems like the mean was not that much less, 1,003.9 versus 1,068. But this is a sample of 592 students. That's a pretty big difference when it's a sample of 592 students. So their mean is pretty significantly, statistically significantly less. So we would reject the null hypothesis. We got a low p-value. So there is enough evidence at the 5% level of significance to say that South Elgin High School's mean SAT score is less than the national average, national mean. Okay, that's that. And that's the kind of thing I'm going to ask you to do on the next test. When we get to it's our last test. We are in our last unit. So exciting. Only 2 more weeks of learning stuff after this, and then we have our last week will just be the test. But I'll want you to do all these 6 steps, and I'll have the points for each part of the process. Okay. Any questions? I feel like I went a little fast there. Are there any questions from the little extra ones here? All right, I'm not seeing any questions. That is it for today. Feel free to email me if you do have more questions. Your homework, like usual, is going to be due tonight in my stat lab, and then quiz on that practice document in D2L on Friday. Let me know if you have any questions. Otherwise, we'll be here again next Monday. All right. See you, everybody. Keep a lookout for exam scores. They will be posted hopefully soon. All right.